Turing never needed an ALU to build a computer. Technically, neither do we. The Turing 6502 runs entirely from static RAM and a state machine. No arithmetic logic unit. No gates beyond the couple of control signals. Here it is, running Apple II Pac-Man in real time. This is a diagram of the architecture, and there's no dedicated hardware ALU. So, why does every real CPU include an ALU? Specifically, the ones we're interested in on this channel: 6502, the Z80, the 8086, and the 68000. If you've ever wondered why the inside of the 6502 looks the way it does, why there's an ALU, program counter, and an instruction register, this series is for you. We'll start with a machine that mirrors Turing's original vision, a rulebook and a notepad. You scan one symbol at a time, then move left or right. Then we added random access to the notepad, and boom, 1,000-fold speed up. Better, but still not fast enough. Next, we bumped up the symbol size to 8 bits, just like the early microprocessors. That finally gave us real-time performance using nothing more than TTR logic, static RAM, and EEPROMs. But here's the cost. Going to an 8-bit symbol exploded the size of the rulebook. The first working 8-bit Turing 6502 needed 8 megabytes of EEPROM. That's thousands of rules, with 256 symbols each rule just to do basic math. In the last video, we added a transfer register, and that helped. We dropped from 8,000 rules down to about 3,000. A big win, but still too big to be practical. By the end of this series, I'm aiming to get the rulebook down to 8 kilobytes of EEPROM space. That's 3 orders of magnitude smaller with the same functionality. Let's see if I can do it. My plan is to add conventional CPU components to the Random Access Turing Machine one at a time, starting with the dedicated ALU. Then we'll add an instruction register, and together I'm hoping that these should radically shrink the size of the rulebook. Finally, we'll add 2 8-bit program counters and a dedicated status register. Let's start with the big picture. At the foundation, we have the Turing machine, the simplest theoretical model of computation, thanks to Alan Turing. On top of that sits the instruction set architecture, thanks to John von Neumann. The hallmark of this architecture is the fetch, decode, execute cycle, something we'll watch closely in action shortly. And here's the cool part. A Turing machine can emulate any other Turing machine. And any machine that can emulate a Turing machine is said to be Turing complete. So, we can emulate a 6502 on our Random Access Turing Machine, and with enough bank switch memory, we could even emulate our Random Access Turing Machine on a 6502. In this video, we'll be using 3 different representations as we walk through the AND instruction. First, the hardware level block diagram of the Random Access Turing Machine, the actual C code that programs the rulebook EEPROM, and the finite state machine diagrams that control the execution flow. Here's how we build the finite state machine, one state at a time. Each call to set single state maps one input symbol and one state number to a single EEPROM entry. But that state number is relative to the last new state machine call. So for example, if the previous state machine ended at 1032, then the AND instruction starts at state 1033. Let's look at how that translates to the actual EEPROM hardware. The offset's 0 in this case, so 1033 plus 0 is 1033, or 409 in hex. That's what we place on address lines A8 through A20. The input symbol becomes the lower 8 bits, going on A0 through A7. Let's say our input symbol's 2 hex. That gives us an EEPROM address of 40902 in hex. So, what gets stored at that address? The data field holds 3 things: the next state, the output symbol, and the control signals. And when I program it, that next state can be either a relative offset from the current block or a jump to another labeled state machine entirely. Now I'll admit, the first time you read this code, it's a bit of a bear. That's because the input and outputs refer to the current state, but the notepad address and control signals are for the next state. Once you get used to the separation though, it starts to click. Now, the visual equivalent of this is the state machine diagram. Each circle is a state. We arrive at a state with 2 things already determined: the notepad register we're going to use, and the control signals like memory read, memory write, and transfer. In theory, each state could have 256 output arcs, one for each possible input symbol. Each arc can specify an output symbol, and that doesn't have to be unique. In fact, sometimes we want all arcs to emit the same output, no matter what the input was. That's equivalent to writing a constant to the notepad or main memory. Finally, just to make the diagram easier, if the relationship between the in symbol and out symbol is pretty obvious, I'll just draw one arc with the default relationship. In this case, the output symbol is the same as the input symbol, whereas in this case, the output symbol is the input symbol incremented by 1. Last time, we looked at the overall architecture of the Turing 6502 built from EEPROMs, static RAM, and logic. Now let's go a little deeper and walk through a real instruction, the AND immediate operation. Here's a list of all the state machines needed to support the 6502 instruction set. You'll notice that many of them require one or two states, but others, like zero-page offset, absolute offset, and indirect Y index modes, each require about 260 states just to perform the 8-bit addition. Then we've got AND, OR, and XOR, another 260 states each. Add and AND with carry, same story. That's over 2,300 states dedicated to operations we could collapse into a single component, an arithmetic logic unit. But before we go to the ALU, let's see how this current machine handles the AND instruction from start to finish. We'll walk through each part of the fetch, decode, execute cycle using only EEPROMs, static RAM, and TTL gates. This is where it gets real. It is a bit of a slog through the mud, but this is a critical battle. So, how does the actual 6502 work under the hood? Well, it continuously steps through memory fetching instructions to execute. In this example, we hit address 87B1 hex, which contains the byte 29 in hex. If we look that up in the instruction table, we find it's the AND immediate instruction. This means we'll take the value at the next memory location, 87B2 hex, which is 02, and AND it with the value in the accumulator. We store the result back in the accumulator, update the status flags, and then move to address 87B3 for the next instruction. Hopefully this is all feeling fairly familiar so far. Let's step through the Turing 6502 machine, beginning with the instruction fetch, which starts at state 105. Now these state numbers are a bit like basic line numbers, arbitrary but necessary. State 105 assumes we've already shadowed program counter low and program counter high into the mar low and mar high registers respectively. In this case, we assert the mRead control signal and tell the notepad to use the instruction register variable, which is at address 9 in the notepad. During the first half of the clock cycle, we perform the main memory read. The value 29 is returned and placed on the EEPROM address lines A0 through A7. At the same time, rule number 105, or 69 in hex, goes on to A9 through A20. Around 50 to 100 nanoseconds later, the EEPROM outputs the next state, 107, the next notepad address, program counter low, and the current output symbol, which is 29. In this case, the output symbol is just the same as the input symbol. How does the EEPROM know to output these values? Well, I programmed it to do that by hand using this code here. Instruction decode branch is our first pass decode. If we scroll down, we see an arc for opcode 29 hex, which tells us to jump to the state machine for immediate mode addressing. These values get latched into the output flip-flops on the positive edge of clock. There's a subtle but important detail here. While clock's high, the register feeding the notepad still points to the instruction register. That's because this register is latched on the negative edge of clock, so it hasn't updated yet. The flip-flops on the EEPROM outputs are latched on the positive edge of clock, so these registers can store different values for half a clock. While clock's high, the output, 29, is written into the notepad's static RAM instruction register variable. This is where we remember the current instruction being executed. Then, the new state 107 makes its way around to the upper EEPROM address lines, ready for the next cycle. Finally, on the negative edge of clock, the notepad register is updated with the variable address for PCL. Remember, PCL points to location 6 within the notepad. So, where are we now? We've just landed in state 107, the addressing mode immediate state machine. We're using program counter low, and we want to increment it. But there's a special case to detect. What if PCL is equal to FF? It needs to roll over to 0 and increment PCH. I could just add some arcs to handle this, but that means different arcs out of the same state will refer to different notepad register addresses. Instead, I want all the output arcs to share the same notepad address. The reason will become clear later in the series when we talk about pipelining. I add a temporary state, a tiny bubble in the pipeline. Yes, this causes a 2-state delay every 256 instructions, but for now I'm okay with that. Back to our machine. In the Random Access Turing Machine, we read from one of the memories while clock's low, and write to one of the memories while clock's high. Clock's low, no memory reads asserted. The value B1 stored in PCL is read from the notepad register, flows through the buffer, and comes to the lower 8 bits of the EEPROM address. The EEPROM returns next state 106, next notepad register is instruction register, and the output symbol is B2. On the positive edge of clock, this gets latched. The B2 is then written back to the PCL register and presented to MAR-low. State 106 wraps around, feeding back into the EEPROM as the new upper address lines. On the next negative edge of clock, B2 is written into MAR-low. The variable 9, which is instruction register, is written into the notepad address register, and we've now completed the addressing mode immediate state machine. We've incremented the program counter, and the memory address registers hold the address of the operand for the next part of the instruction. On our state machine diagram, we've done this part of the AND immediate instruction. Up next, the second pass decode, where the instruction is actually executed. Let's just take a moment and trace out our path so far. State 105 is first pass decode, where we read the instruction. What we do next depends on what the instruction does, but in this case, we need to increment the program counter to point to one of the operands. That took us through state 107. We missed states 108 and 109, which we only use if the instruction crosses the 256-byte page boundary. Either way, both paths take us to state 106, which is our second pass decode. In this phase, we're reading the instruction again, but not from main memory this time. Now, it comes from the notepad, specifically the instruction register variable. 029 hex travels along the data bus, passes through the buffer, and lands at the EEPROM inputs again, this time paired with state 106, which is 6A in hexadecimal. The EEPROM looks it up and outputs next state of 1033, next notepad address is the B register, and the output symbol is 29. We latch these values on the positive edge of clock. Note that mread is now asserted, but we won't use that until the next clock cycle. While clock's high, we write 29 hex back to the notepad. Now, technically I don't need to do that. We don't use the instruction register until we load a new value in the next instruction. But for now at least, I'm sticking to Turing's convention of performing a read followed by a write every clock cycle. Now, state 1033 moves around to the EEPROM input lines. State 1033 is our AND operation in second pass decode. It doesn't matter what addressing mode we used in first pass decode. All of the AND instructions go through state 1033 in second pass decode. Whether we used immediate mode, zero-page addressing, or one of the more complex ones like wide direct indexed addressing. What we do know is that in state 1033, the memory address registers point to the location of one of the operands for the AND operation, and we need to do a main memory read to load into the B register. On the negative edge of clock, B reg is latched into the notepad address register, and this time we perform a main memory read from 87B2 hexadecimal, which holds the operand value 02. This operand now becomes the input symbol for our next EEPROM lookup. Here's the clever bit. The EEPROM is set up so that the next state is 1034 plus the operand value. In this case, it's 1034 plus 2, which is 1036, but it could be anything from 1034 to 1289 depending on the operand. So the operand effectively chooses which of 256 execution paths to take next. In state 1033 with input symbol 2, we output 1036, A reg, and 2. On the positive edge of clock, the data is latched into the output registers. The operand 2 is written into the B register of the notepad. The new state, 1066 in decimal, is fed back into the EEPROM. On the next negative edge, A reg is latched into the notepad address register. When clock's low, we read the accumulator value, let's say it's 8B hexadecimal, and that goes back to the EEPROM as the input symbol. Now, this is the moment where the actual AND takes place. We're in state 1034 plus operand, and the input symbol is the accumulator. This gives us a unique operand accumulator pair. We know that 02 ANDed with 8B gives us 02, and that's what we see as the output symbol on this arc. We pre-compute all the values of A and B and write the result as the output symbol. This is essentially a 16-bit lookup table, 8 bits for the operand and 8 bits for the accumulator, starting at address 1034. So instead of using logic gates to compute A and B, we pre-compute all possible answers and just store them in the EEPROM. The AND operation isn't computed at runtime, it's remembered. The EEPROM now outputs the result of the AND operation. In this case, we're ANDing 8B with 2, which gives us the result of 2. On the positive edge of clock, we latch state 33. The result gets written into the A register variable in the notepad, and the next notepad address is the status register, because we still need to update the flags. Now, here's where things get interesting. From the 6502 instruction definition, we know that only the negative and 0 flags are affected by AND. Depending on the result, we can branch to one of 3 possible states. Clear negative, set 0 if the result's 0. Clear negative, clear 0 if the result's between 1 and 127. And set negative and clear 0 if the top bit's set, so values 128 to 255. In our case, the result's 2, so we go to clear negative and clear 0, which is state 33. While clock's high, we write the answer 2 into our A register variable. We loop state 33 back around to the EEPROM inputs. On the negative edge of clock, we set the notepad address to the status register and read the current status register, which is B5 hexadecimal. Now we want to execute this part of the state machine to close out the instruction. In state 33, we AND whatever we've read with 7D to clear the negative and 0 flags. So B5 becomes 35. At this point, we need to increment the program counter, and we go to state 104, which is a dummy state. Now, the reason that's there is because we want to pipeline the architecture later, and we don't want the memory read to be immediately after setting the memory address registers. But more on that later. In state 104, we set up state 105 to do a main memory read into the instruction register, and there we have it. We're back at state 105, which is where we began. We've just done one complete loop of the fetch, decode, execute cycle. Back to the block diagram, we've just read B5. This occurs while clock's low, and the B5 finds its way along the data bus back to the EEPROM input. In state 33 with B5, the EEPROM outputs next state 24, PCL, and 35. Clock goes high. 35 is written back to the status register. State 24 loops back to the EEPROM inputs, which is the start of fetch. So on the negative clock edge, program counter low is latched into the notepad address. Almost done, but there's one last bit of housekeeping. The memory address registers still point to the operand. We need to bump them forward to point to the next instruction. While clock's low, we read B2 hexadecimal. With state 24 and B2, the EEPROM outputs are next state of 26. Notepad address is program counter high, and the output symbol's B3. On the positive edge of clock, the values are stored in the output flip-flops. Then, B3 is written into the program counter low variable and presented to the memory address low register. State 26 loops around. Next, program counter high is latched into the notepad address. B3 is latched into MAR low. Then, While clock's low, we read the 87 hexadecimal. With state 26 and 87, we output next state 104, output symbol 87 hexadecimal, and notepad address temp register. On the positive edge of clock, this is copied into the output registers. While clock's high, 87 gets written back to the program counter high variable and presented to the memory address register high. On the negative edge of clock, temp is latched into the notepad address register and 87 is latched into mar high. We loop 104 around and we're set up for the next cycle. Now you might be wondering, why did I bother touching program counter high when it didn't actually change? Well, here's the reason. In other addressing modes, the memory address register might be pointing anywhere, like, for example, 0052 in zero page mode. So I always refresh MAR high just to make sure it reflects the current program counter correctly. Finally, we hit state 104, which is just a dummy state. We read the temporary variable, which I'll just call 0 for now. The EEPROM outputs 105, instruction register, and whatever it read is the input symbol. On the positive edge of clock, these are latched into the output flip-flops. 0 is written back into the temporary register variable. And on the negative edge of clock, iReg makes its way back into the notepad address register. That's it. We've just executed an entire AND instruction from fetch to flags on a machine made entirely from EEPROMs, static RAM, and logic. Now here's the big insight. We just use a 256 entry lookup table where each state handles 256 input symbols. That means this one operation and took 256 states, and that's not including fetch, decode, and status update. The downside? Space. It eats up huge proportions of the rulebook. In the next video, we're going to bring in a real ALU, one I built in another series, and use it to replace this lookup logic. Let's see how much we can shrink the rulebook by. Before we finish, I want to show you how I plan to add the ALU to the machine. We connect the ALU module to the data bus. We use control lines from the finite state machine to decide when data is latched into the ALU hold registers and when the ALU is allowed to write its output back to the data bus. Another set of finite state machine lines select the operation that the ALU performs. For now, I'll assume the ALU is hardwired to do a simple AND operation, although eventually it'll depend on the instruction. So join me in the next video to see how much impact adding the ALU has.